It's time for Calculus Section 8.3. We're going to do this in 4 videos this time because there's some different topics. And the first one is going to take a little bit longer because we've got a little warm-up and just need to explain the process a little bit, and then we'll do some examples. So to start off with, I do have a warm-up for today. This is just a basic skill that you're going to need in order to be successful in this section. So they're going to seem fairly simple, but give a formula for the area in terms of x. What would the area of a square be? That one should be done already. What would the area of a semicircle be? So be a little bit careful with that one. And then also with a semicircle of diameter x. So you're going to have to figure that one out. So pause the video, answer those questions, and check them in a moment. Here are the answers to the warm-up today. You should have got x squared for the first one. Area is pi r squared for a circle, but r is x. It's a semicircle, so we have to cut it in half. So it's pi r squared divided by 2. A semicircle, you have to divide the diameter by 2 before you square it, and then also divide it by 2 because it's a semicircle. That's where the 8 comes from. All right, so for this lesson 8.3, we're going to cover volume as an integral. That's like the main idea of what this section is about. So I'm going to explain what that means. And then this video is going to do known cross sections. And then video 2 will be the disk method, 3 is the washer, and 4 is the shell. The book kind of defines it a little bit differently over here. So I'm not following exactly in the order that they do, but this makes more sense because basically this last section here goes better with today's than the middle stuff. Anyway, so we're going to figure out the techniques to find volumes of solids in 3 dimensions. If you are in 3D modeling, you might like this lesson because you could actually calculate the volume of your 3D models depending on how complicated they are, but could connect to that a little bit. So here's what we're going to be doing today. We're going to be finding the volume of a solid on a coordinate grid. So for cross section, we're going to basically take the solid and slice it into pieces. The slices are called cross sections, and each cross section is going to have a width of delta x, and that's going to, we're going to find the limit as delta x approaches 0. So that's going to be the integral. And that if we add up all these little slivers of cross sections, then we would have the area of the shape. This one is delta x. This one is delta y, just because it's the other direction. These graphs are a little hard to see because of the way they're moved, but this one is a nice square that would change as it went down, and it would always be like a square shape. This one has a curve on the top, so this one would be a little harder to find the area of because it's going to curve and be longer and longer and longer, and then shorter and shorter and shorter as it goes across. So this is like a visualizing lesson, and you really are going to want to draw some pictures. I know they won't be beautiful. Well, maybe they will be. That'd be wonderful. There's also some ways to computer generate these, but I'll do the best I can in my drawings. So the method that what you want to do is first draw it. You want to sketch the solid that you've got, like the base or the function that they give you, and then the cross section. The cross section is going to be things like squares and semicircles and triangles, maybe rectangles. So that's why that warm-up was in there, just so you have those formulas kind of down. You're going to find the formula for the area of that cross section. So again, the warm-up, if it's a square cross section, your formula is x squared. Your limits of integration, so from where to where are we doing this? And then once you have it set up, you just calculate it. At this point, you should know how to calculate your integrals. If it's a simple one, I recommend doing it by hand. And if it's complicated, use your calculator. But most of these are going to be able to be done by hand, I think. So this isn't really about learning how to integrate. It's all about setting up the problem. So let's get started with our first example. Here's a pyramid that's 3 meters high. So it's turned on its side here, but it's got 3 meters high, has congruent triangular sides and a triangular square base that's 3 by 3 meters. Each cross section is parallel to the base and it is a square. So here's this red one or pink one in the middle here is an example of one cross section. Find the volume of the pyramid. So the idea here is if we take all the area of this square and the one next to it and the one next to it and the one next to it and the one next to it, we add them all up, we will get the volume of this pyramid. So the first thing you want to do is draw it, which we have a nice little picture. The second thing is find the area of a cross section. So the area of a cross section would just be x squared. And then the third step, let's just go back to those real quick, is find the limits of integration. Where are we integrating? From 0 to 3. Because that's the smallest little square I have up here would be 0 by 0 by 0, which is kind of silly to even think about drawing. And then the biggest one on when I get down to this end will be 3 by 3. So I'm going to integrate from 0 to 3, and my formula is x squared. So I need to integrate from 0 to 3, x squared dx. And that's pretty much it. So the answer to that, what is the antiderivative of x squared? 1/3 x cubed, and we're evaluating that from 0 to 3. So I plug in a 3 in there. 3 times 3 times 3 is 27. Divided by 3 is 9. And then minus 0. So the answer is 9. Because this is volume and my units are meters, I would put meters cubed. All right, that concludes our first example. I'm going to kind of show you the steps that they have you walk through, just so you kind of get a little, that was kind of a fast version, but it was also a simple problem. First of all, draw it. Notice that the interval is from 0 to 3, and a typical cross section is this drawn x. Then the next thing they have you do is find the formula, which is x squared. The limits go from 0 to 3, and then you do the integration that we just did here. All right, let's look at another example. Here we have a solid that is made so that its base is the shape of the region between the x-axis and one arc of the curve 2 sine of x. The wording can be a little tricky, so make sure you read that carefully, draw what they're talking about. So we've got the first curve of 2 sine x, so sine x that's been stretched up a little bit. They laid it flat so the picture would make more sense. And then they're going to tell you what the cross sections are. The cross section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. So these are the diameters, which are drawn here in this picture. So this is a nice little picture. If you imagine all the slivers, you'd get this fun little curve shape, almost a boomerang, but it doesn't have like an inside. So we're going to find the volume of this. All right, so let's start with the first step. What is the area of the cross section? Well, a cross section is a semicircle, and a semicircle is pi r squared divided by 2, because it's half of it. But what is my radius? What is my radius on this graph? Well, it's the height of the function divided by 2. And the value of my function each time is 2 sine of x divided by 2. So that means the radius is sine of x. So my formula for the area of a cross section is pi sine squared over 2. Okay, so that's it. I found the area. Now I need to just integrate that from, they said the first curve, so it goes from 0 to pi. So from 0 to pi sine squared of x over 2. By the way, that pi over 2 is just a constant, so I could put it out here instead. That will make my integration much easier. All right, I think I have an answer sheet over here just to help me with that integration part a little bit faster. So we got our volume. We need to do the antiderivative of sine of x squared, or because that's kind of a difficult one, we can just put this one in the calculator. So do math 9, you can do this, in the nice calculators, they have this notation. Otherwise, in the older calculators, you have to put it in. And then don't forget to multiply that by pi over 2 that's in the front, and you get pi squared over 4. If you Yeah, anyway, you can leave it as whatever that decimal is also, that's fine. Don't forget your units on the AP Calc test. They're going to be really picky about that. So make sure that you put your units there. These are volumes, so you're going to have cubic units. All right, here's another example. Find the volume of the solid whose base is bounded by this circle. So the circle, x squared plus y squared equals 4. So a circle with a radius of 2 is my base. The cross sections to the x-axis, they're perpendicular to the x-axis. So they go this direction, and they're squares. So this is a standing up square. And right here we'd have a bigger one, and over here on the sides we'd have like little squares. Okay, I'll just draw a few of them kind of at the same angle so you can try to see. Visually, it would be a whole bunch of squares sliced together there. Little ones to bigger, then back down to little. Hopefully you can visualize that a little bit. So how are we going to solve this problem? Well, first of all, we want to find the area of one of these cross sections. Well, first, how high it is, we probably need to know what this function is. We have a circle, but we need to solve it for y. So let's get y squared by itself first. 4 minus x squared, and then we square root it. So on the top half, we need to have a function. So the top half of this circle is y equals the square root of 4 minus x squared, and the bottom is y equals negative the square root of 4 minus x squared. Okay, so how far is it from here to here? What is one of these lengths of my square? It would just be the top minus the bottom. Just going to show you real quick. So to do that, if we did the top minus the bottom, it would just be double, minus a negative, right? So we have 2 of those. And then I'll just go back to my picture because that didn't. All right, so the area is the square root of 4 minus x squared minus the bottom one is negative square root of 4 minus x squared. So we have this double negative here, and that's where the 2 came from. Okay, so the area of one cross section has a base of that, but sorry, that was just this height. So then I need to square it, right? Squared. That's my radius, or it's not really a radius. It's the base of my square, and then my height would be the same, so I square it. Okay, now I just need to figure out my interval of integration, and it has a radius of 2, so I'm going to go from -2 to 2. -2 to 2. If I square this thing, I'm going to get 4 times 4 minus x squared dx. Now I'm just going to solve that. 4 times 4 is 16 minus 4x squared dx. This 16 can't pull out because it's subtracted here, so just be careful. You can only pull out multiples. I could actually pull out that 4 multiple. Yeah, well, already did this. Antiderivative of that is 16x. Antiderivative of that is 4/3 x cubed. Evaluate that from -2 to 2. Or at this point up here, put it in your calculator and see what you get. This problem was already done over here. So when you calculate that, you get 128/3, and the decimal version of that is also acceptable. Make sure if you do, you round to your 3rd decimal spot, or at least include to the 3rd decimal spot. Okay, I'm going to go ahead and post a few more examples here. I'm not going to take as long to work through them, but I wanted to just give you some practice at setting them up. So I'm going to put an example up here. Pictures may or may not be started for you. This one does have a triangle because it doesn't explain it in the problem. And then you can go ahead and work out the problem, pause the video, and then come back and I'll be putting the answers up in just a moment. So this one is find the volume of the cross sections perpendicular to the y-axis of a right triangle. They are semicircles, so not a great English sentence there, but here's your right triangle. It is not to scale, as you can see, the 4 and the 3. They are semicircles that are perpendicular to the y-axis. So when you draw this, you're going to have semicircles that go up like little humps with a diameter of this width right here because it's perpendicular to the y-axis with a bump. So you draw it, you see if you can find the volume of that solid. All right, so the work has been done for this one. Here's a picture to give you a little visual of those semicircles. We would need to find the equation of this line first so that we know how wide each of these are. So the equation of this line is 4/3 x minus 3. Solve it. Oh, they did it in terms of x this time, or in terms of y, because the height here, if you turn your head sideways, is from here to here, and we're going to integrate from here to here because they're sliding this direction. You don't want to do this in terms of x. So we take that equation, rearrange it for x equals, so that we have a y thing. And then for a semicircle, we did that in the warm-up at the beginning of the lesson. The semicircle will be half of this, pi r squared, and then divide that by 2. So that was where the 1/8 came from. So I think they took this equation, cut it in half, and then made pi r squared. It's 1/2 pi r squared of that radius squared. Then you integrate that. Where are we integrating it from? From 0 to -3 would give you a negative answer, so they just went from -3 to 0. If you did it from 0 to -3, you would just put a negative and make that a positive. We've got volume. It's going to be a positive answer for volume. And there are no units on this, so don't worry about your units. Okay, on to example 3. Oh, sorry, this is actually a digital picture of that. So here's your right triangle and your semicircles. And so it would make like this kind of a slanted half cone shape. So you can get some pretty interesting shapes with these volume problems. All right, here's another one. Find the volume of a solid whose base is bounded by a circle and the cross sections are equilateral triangles this time. You might have to use a little Pythagorean theorem or something to figure out the height of those triangles. So take some time, figure this one out, and I'll put the answer up. All right, so we have these equilateral triangles. Just like last time, they are the height of one base of that triangle is top minus the bottom, so 2 of those. So there's my 2 of those. And then to figure out the height of this thing so that we can do area of a triangle, you have to use the square root of 3 over 2, like for trig. So anyway, so there's where that came from, and then you can calculate that. You can also do half of this, so you could treat it like a right triangle, do half of the circle, and then just double your volume because you know the top half and the bottom half are the same. So that's where this one-sided thing came from right here. All right, example 4. Pause the video, see if you can draw it. Very similar to the last problem. Circle base, but the cross sections are isosceles triangles with one leg as long as the base. So they look like this instead. And here is the answer to this one. Base times height. So since I have the base, it's basically half of the square problem that we did earlier. And for the last example, I've got a volume of a solid bounded by 2 different functions. So you're going to want to graph both of those functions. And then the cross sections are perpendicular to the x-axis and they're rectangles, always with a height of 5. Pause the video, see if you can draw or visualize a picture of what that would look like and solve the problem. All right, so first you're going to want to graph those 2 functions, and then the height of each of these, or width of each of these rectangles, will be the difference between the 2 functions. So we're going to take the line minus the parabola to figure out what this width is every single time right here. And then the height is always 5. So this 5 is here. If the height was changing, if it was a square or something, then we would have a different number. But because that's the height, it's a 5. Integrate that. You can do this one by hand or with a calculator. Pull the 5 out if you're doing it by hand. And that's it. So that concludes part 1 of lesson 8.3.